In this video, I'm going to give you some tips for solving the ALEKS problem called identifying the intermolecular forces between atoms, ions, and molecules. So this problem is going to give us two different substances, either an atom or an ion or a molecule, and it's asking us to list all of the possible intermolecular forces that could exist between these two things. Now, first of all, here is a list of the 4 intermolecular forces that ALEKS recognizes. One of the things that's going to be tricky about this problem is that chemists aren't super consistent with the way that we describe intermolecular forces. So for example, your textbook might use the phrase dipole-dipole. ALEKS isn't like that. ALEKS wants you to just say dipole. So this notation here, this is exactly what ALEKS likes. This is what's going to make ALEKS happy. Make sure that you use this exact notation. Don't forget the hyphens in between hydrogen bonding and ion dipole. And don't use any other terminology, even if that's what you're being taught in your classroom. Now, what I'm going to do is give you a set of steps to follow to determine which of these intermolecular forces you have between your two molecules. First of all, number 1, everything has dispersion forces. I'm not even going to write that down. Everything has dispersion forces. This should always be the answer. One of the IMFs that you have in your substance, always right off the bat, write dispersion, because that's one of the things that you have. The easiest thing to look for is the ion dipole force, and that is because in order to have the ion dipole force, you have to have at least one ion that you are comparing. So ask yourself, do you have an ion? And ALEKS is not hiding these ions from you. If you have an ion, it's going to be obvious. You are either going to get a formula that has a charge on it, and then you're going to know, yeah, that's an ion, or ALEKS is going to use the word ion. And they both of them do not need to be ions. It only takes one. Only one of them has to be an ion. If you have an ion, so I'm actually going to change this to say if you have an ion, then you are going to have the dispersion forces, because everything has that. I'm just going to abbreviate it, DISP. You are going to have the ion dipole force as well. The ion dipole IMF is the IMF that exists when you have an ion. So those are your two. If you don't have an ion, then the next thing that I want you to look for is whether both of them are atoms. So if both of them are just single atoms, and that is something that pops up quite a bit. So that could be maybe like helium and krypton, maybe is what you get. Be careful that they're not atomic molecules. Like Br2 is not an atom. That's a molecule. It is made up of one type of atom, but that's not an atom. That's a molecule. Just Br, that would be an atom. So if both of them are atoms, then all that you have in that case is just the dispersion forces. And those are two that are relatively straightforward. Unfortunately, most of the questions are not quite that easy. Like mine, that's not an ion, that's not an ion, and also not atoms as well. So then we're going to have to be a little bit trickier. So if you don't have an ion and you don't have just simple atoms, the next thing that I want you to do is look up or draw the Lewis structures for both of those molecules. And I do encourage you, just to save time, even if you're really good at drawing Lewis structures, I do encourage you to use the internet to look those Lewis structures up for you, which is what I'm going to do. So I'm just going to go, see, I've got NOCl's Lewis structure right here, and I'm just going to copy it right there. Don't forget the lone pairs. And then the Lewis structure for chlorine monofluoride. That is, chlorine monofluoride is ClF, but you could also type in chlorine words, chlorine monofluoride, and we can see that it's kind of a funky structure there. Doesn't have the bond drawn out, but that is a single bond between the chlorine and the fluorine. So there's its Lewis structure. Okay, so why are we wanting to have Lewis structures? Why do we need the Lewis structures? Because the next thing that we're going to be looking for is the potential for hydrogen bonding. And that's going to be our third thing that we're going to try to find. If both of these substances can hydrogen bond, I'm going to abbreviate it H bond, Then, in that case, what you're going to have is, of course, dispersion, because everything has dispersion. You are also going to have hydrogen bonding. I'm going to abbreviate it, but you won't abbreviate it. And you're also going to have the dipole force. Hydrogen bonding and dipole forces go hand in hand. If you have hydrogen bonding, you always have dipole, although not the other way around. But if you have hydrogen bonding, you also have dipole. So let's take a look at my molecules. Can these hydrogen bond with each other? Well, in order for my molecules to hydrogen bond, I have to have a hydrogen atom, and I don't have a hydrogen atom anywhere, so my molecules are not capable of hydrogen bonding. In order for you, hopefully you know how to identify hydrogen bonding, but just as a reminder, a hydrogen bond requires one of our molecules to have an HO, an HN, or an HF bond, and our other molecule needs to have either an oxygen, a nitrogen, or a fluorine, and that makes them eligible for hydrogen bonding. So if both of them can hydrogen bond, then there you go. Now, if none of these apply, like in my case, I don't have ions, I don't have single atoms, they are not capable of hydrogen bonding, then probably, and I'm going to put a big asterisk next to that, probably what you have are dispersion forces and dipole forces. In order for that to be actually the correct answer, then the molecules need to be polar. So if they are polar, but no hydrogen bonding, then your answer is going to be dispersion and dipole. And this is actually, the reason I have it on here last is because this is the one that's the most tedious to analyze. Are the molecules polar or not, yes or no? Because there's a lot of variables that we have to consider when we're trying to determine if molecules are polar. First of all, we have to determine the difference in electronegativity between the atoms in every single bond in each molecule. So we need to look at the difference in electronegativity between the oxygen and the nitrogen, also between the nitrogen and the chlorine, and also between the chlorine and the fluorine. And then we also have to take into consideration the three-dimensional shape of these molecules. It's a pretty tedious process. I'm not going to go into how we go about identifying whether or not molecules are polar. I do have videos on that, and a lot of people have videos on that. So if you need a refresher on how to determine if a molecule is polar or not, then I encourage you to go find that. But in general, and it's kind of a safe risk, if a molecule is asymmetrical, meaning like this molecule here, I've got a nitrogen in the middle and I've got two different atoms attached, typically, not always, but typically, like if you're in a crunch for time, that molecule is probably polar. This molecule with two different atoms also, it's probably polar. Again, it's not a guarantee. Don't come at me in the comments if you know you're doing that and it ends up being wrong. It's not a guarantee. But if you're in a rush for time and you don't have time to go back and review what it means to be polar, it's a pretty safe bet that when you're looking at an asymmetrical molecule, it's probably polar. And that is the case for mine. My molecules are polar, and that means that I have dispersion forces and dipole forces. Now, this is a pretty tricky problem, and take your time with it. Definitely use the internet to help you look at these Lewis structures. Maybe you're going to have to take some risks down here, but I know you can get through it.